Hi, thanks for joining me today. I've got a fun geometry problem. We have S, a set of 5 different positive integers, the largest of which is m. And we're told that it is impossible to construct a quadrilateral with non-zero area whose side lengths are all distinct elements of S. What is the smallest possible value of m? So we have a set S, maybe with some different positive integers in, maybe 2, 8, 3, 7, and 11. And these are the 5 different positive integers in S, and we're told that we can't construct a quadrilateral with non-zero area from this using these numbers as the side lengths of the quadrilateral. And it turns out that this S is actually no good because we can easily construct a quadrilateral with these as the side lengths. Maybe the base here would be 8, maybe this side length here would be 7 or something, maybe 2 here, and then like 3 here, something like that. So it doesn't have to be regular or have any certain properties apart from it's a proper quadrilateral. So we want to find a set S where we cannot construct a quadrilateral from any choice of 4 numbers as the side lengths. And we want to do it in such a way so that the largest value of S, i.e. the m value, is as small as possible. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so we're going to begin our solution by actually reminding ourselves of the triangle inequality. So this says that if we have a triangle with side lengths A, B, and C, then A plus B must be bigger than C. And in particular, notice that we haven't defined which sides are A, B, and C. So even if we choose A and B to be the smaller two sides, it must be that A plus B is bigger than C. Now, firstly, why is this true? Well, hopefully it's pretty clear that this is true if either A or B is the biggest side of the triangle, because then A plus B is definitely going to be bigger than B, and if B, let's say, is the biggest side of the triangle, then it's definitely automatically going to be bigger than C. What happens if A and B are the two smaller sides of the triangle? Well, that means that C must be the longest side. So if my triangle looks like this with the base C, now if I want this to actually be a triangle, when I connect my two other sides, so let's say this one here is the side A, it's impossible for A and B to both be too short, because otherwise these sides will never meet up. And so we think about, well, what's the shortest that A and B can be? Well, it's so that they just touch. And that's going to be when I have C like this and A just be ever so slightly above. So that side length there is A, and then this side length here is B. But you can hopefully still see that A plus B must be ever so slightly bigger than C for this to work. Because if A plus B just equals C, you're going to kind of get a straight line where that's A and that's B. So it technically won't be a triangle because we require non-zero area here. Anyway, this is the triangle inequality, which is pretty famous. But now what we're going to introduce is what I'm going to call the quadrilateral inequality, which is basically the same thing, but for quadrilaterals. So if we have a quadrilateral with side lengths A, B, and C, so A, B, and C are A, B, C, and D, sorry, are the side lengths of my quadrilateral, then I must have that A plus B plus C is bigger than D. And this is for the exact same reason. Again, if A, B, and C, if one of those are the longest sides of one of the longest sides of my quadrilateral, then this is automatically true. What if D is my longest side? Well, we'll call that D. And then again, in order to ensure that this quadrilateral it has a positive area, we must have A maybe here, B could be there, and C could be there, but we still require A plus B plus C to be bigger than D, because if it was less than or equal to D, we would not be able to connect these dots like this and create a quadrilateral with positive area. Okay, so this is a triangle inequality and the quadrilateral inequality, and hopefully it's actually not too difficult to see how we could kind of extend this to the n-gon inequality. So if I have an n-gon inequality, this would be, suppose my side lengths of my n-gon were, let's say, a1, a2, all the way up to an, then a1 plus all the way up to an minus 1 would have to be bigger than an. So that would be my n-gon inequality, but that's actually not too important for this problem. We're going to use this quadrilateral inequality. But let me clean up the whiteboard and we'll continue. Okay, so for this problem we need to work out the smallest value of m. And remember, m is just the largest number in S. So let's choose our set S to be as small as possible, to contain the smallest positive integers. So we'll go 1, 2, and 3. And now we could try and put 4 in, but then all of a sudden we break this property that we want it to not be able to construct a quadrilateral. And from our quadrilateral inequality, we can definitely construct a quadrilateral with side lengths 1, 2, 3, and 4, because 1 plus 2 plus 3 is definitely bigger than 4. So we need to think about this fourth element a bit more sensibly, but we don't actually have to think for too long. We just go, okay, let's go back to the quadrilateral inequality. We know that if we don't want to make a quadrilateral from these 4 side lengths, I need this thing here to be sufficiently big so that 1 plus 2 plus 3 is still less than or equal to this number. And I go, well, 1 plus 2 plus 3 is 6, so why not just make this 6? Cool. So this set S with currently 4 elements in cannot construct a quadrilateral with non-zero area. So what I do is I now go and think about a 5th element. And I go, well, we're going to apply the quadrilateral inequality again. And go, well, I want to not be able to construct a quadrilateral with a side length of whatever this number is, and then 3 other side lengths out of these 4 numbers here. And I go, well, if I want this number here to be bigger than 1, 2, 3, and 6, and I want it to be such that it's also bigger than or equal to any sum of these 3 numbers, well, let's just choose the sum of these 3 numbers to be as big as possible, i.e. choose 2, 3, and 6. And if I do 2 plus 3 plus 6, that's 11. And so that means that this fifth number here has to be at least 11 in order to not obey the quadrilateral inequality. And so, again, we're trying to minimize it, so let's just choose it to be 11. And this works, because no matter which 4 numbers I choose from here, the biggest one will always be bigger than the sum of or bigger than or equal to the sum of the 3 smaller side lengths, and therefore, from the quadrilateral inequality, it's impossible to construct such a quadrilateral. And so this would be my set S, and my answer to this question would be n equals 11. But in fact, it's really not too difficult to generalize this result and say, well, what if instead we were looking at 6 different positive integers? Well, then we just build our set and again just use the same property and go, well, 3 plus 6 plus 11 is 20. So this side length here would have to be at least 20. So if we're trying to minimize it, we'll make that 20. And then we'll go 6 plus 11 plus 20. And then that would be what, 37. And we keep going on like this, and we'd, until however many, whatever numbers here, and we'd be able to construct another set with this same property, which I think is quite cool. And this, if you stare at this, you might think, this seems kind of similar to the Fibonacci sequence. And it kind of is, right? You're just summing up, instead of the previous 2 terms, you're just summing up the previous 3 terms. So 2 plus 3 plus 6 gave us 11, 3 plus 6 plus 11 gives us 20, 6 plus 11 plus 20 gives us 37, and so on. So as an extension, maybe you can start to think, well, what if I change this number from 5 to n, and think about this number as n tends to infinity? Because we know that the formula for the nth Fibonacci number has quite a nice form. Maybe this one does as well. And maybe we can start to think about, what if I change this from a quadrilateral to an n-gon? Maybe I'll make this an m, so that those two don't have to be the same. What happens if I change it to an n-gon? And we can think about this n-gon inequality, which basically says that if the side lengths of an n-gon are a1, a2, and so on all the way up to an, then it must be that a1 plus a2 plus all the way up to an minus 1 is bigger than an. And so then it's not too difficult to choose your set. You'll just make, if I give an example with, let's say, n equals 10, I'd choose my first 9 elements to be 1, 2, 3, all the way up to 9. And then my next element would have to be the sum of all of these guys. So 1 plus 2 plus 3 plus all the way up to 9, which would be 45. Then I'd do 2 plus 3 plus all the way up to 9 plus 45, which would be 89, I think. And you'd keep doing this and you'd create another set, S. Anyway, this is some interesting problems for perhaps for you to think about and maybe discuss in the comments. I will stop waffling on about this problem. I think it's a pretty cool problem. Do let me know your thoughts, and thank you for watching. If you are new to the channel, please do consider subscribing. But that is all for now. I will catch you in the next one. Have a great day.